Hello, everyone. My name is Luke McLaughlin. Thank you for joining my talk today. Today, I'm going to tell you about the impact of dilution temperature on size-resolved aerosol emissions from lignocellulosic biomass. Here's an outline of the topics. However, let's get right into the introduction. Biomass burning is a multi-step process that includes drying, devolatilization, and oxidation of volatiles and char. Biomass burning events produce significant quantities of soot and organic particulates, which are known to influence local air pollution and weather, influence global radiative forcing, and have negative health implications. Here in the United States, some major biomass burning sources include wildland fires and prescribed burns. Recently, wildland fires have been in the news due to the devastation that they've been causing on the ground, as well as in terms of the emissions that they've been putting into the atmosphere. And you can see the magnitude of the problem we're facing in terms of the active number of wildfires at the start of the month of September, shown in the plot on the right-hand side. Now, this trend that we've been seeing in the news is also supported in the literature in that recent studies have shown increased fire frequency, larger areas burned, and lengthened fire seasons. We know that the smoke emitted from these wildland fires and biomass burning events influence global radiative forcing, visibility, and health effects, and we know that each of those are affected by the particle composition and size distribution, where composition and size distribution of aerosols are affected by, among other things, combustion efficiency, dilution rate, temperature and relative humidity, concentrations of particles and gases near the event, and the fuel type that's burning. Now, in addition to that, particle emissions can be volatile, semi-volatile, or non-volatile. So when you add all that up, the complex burning scenario creates quite some difficulty in predicting emissions, specifically particulate emissions. So with this in mind, in this work, we focused on pyrolyzing the major constituents of lignocellulosic biomass and biomass samples in a controlled lab setting with the intent of investigating sampling conditions' influence on aerosol emissions, specifically in terms of size distributions, emission factors, and general aerosol volatility. Lastly, we developed an additive model for particulate emission prediction from lignocellulosic biomass pyrolysis. All right, the methodology. In this work, as I mentioned, we're going to pyrolyze samples, and so we achieve that via a TA Instruments Q500 thermogravimetric analyzer. Here, fitted with an evolved gas analysis furnace, which is inert to devolatilization products. Our heating procedure was quite simple, and it's shown in the plot at the bottom of the slide. What I want you to note is that the sample was in a completely inert nitrogen environment throughout the duration of the pyrolysis test, and the maximum pyrolysis temperature reached was 600 degrees Celsius. Once our samples exit our furnace, they're going to be rapidly diluted with preheated lab air. And the dilution ratio, which is the ratio of the sample flow rate to the dilution air flow rate, is 1:67. And in this work, the variable that we're going to change is the dilution air temperature. So here it will be varied at 22, 45, 100, and 120 degrees Celsius. Once emissions are diluted, they will be maintained isothermal through the point of detection, where in this work, the emissions will be detected using a cascade impactor, which has 14 stages of resolution between 6 nanometers and 10 microns. And this instrument will allow us to realize real-time aerosol formation rates, which then, over the duration of the pyrolysis experiment, can be converted to number and mass emission factors. The samples that we're going to pyrolyze, as I mentioned, include the major constituents of lignocellulosic biomass, which are cellulose, hemicellulose, and lignin. And then the lignocellulosic biomass samples that we're going to look at here are lodgepole pine and corn stover. Whereas for brevity today, I'm just going to present my lodgepole pine results. And then for each of our constituent samples, as well as our native biomass samples, the starting fuel mass was on the order of 0.5 milligram. Once we collect our individual constituent data, we're then going to simulate the emissions from a biomass just using the constituent emissions data. And we're going to do that via a simple superposition technique as represented by the equation on the slide, where Y constituent represents the mass fraction of the constituent in the biomass to be represented, and EF constituent represents the number or mass emission factor determined in this work for the corresponding constituent. And on the right-hand side, you can see the constituent makeup analyses of the two biomasses in this work, and this was performed by the National Renewable Energy Lab in Golden, Colorado. Okay, let's look at the results. So first, we're going to look at the number emission factor size distributions for our individual constituents, starting with our cellulose. So on the y-axis, we have a number emission factor, which is the number of particles formed normalized for the starting fuel mass. And on the x-axis is the log scale of aerodynamic diameter. And currently, you're seeing the results for a dilution temperature of 22 degrees C. I'm now going to show you 45 degrees C, 100, and 120 degrees C. Now that you have an idea of what's going on in this figure, I'll show you the results for lignin as well as hemicellulose. And what I want you to observe here are a couple of things. First, we observe that the hemicellulose emissions are much less prominent compared to those of lignin and cellulose. And for each of the constituent samples, we observe that the bin with the most number of particles is the smallest aerodynamic diameter of detection, suggesting that a predominant fraction of the aerosols formed in this work were nucleation mode particles. Okay, so now what we're going to do is take the number emission factor size distribution that you just saw, and what we're going to do is sum up all the data points on each colored curve in this figure. And then this will allow us to see the total number emission factor now as a function of dilution temperature on the x-axis. We can see a similar result for lignin and hemicellulose. Now, what I want you to observe here is one, that the cellulose and hemicellulose number emission factors decrease with an increased dilution temperature, whereas our lignin sample exhibited little to no dependence on dilution temperature. Okay, so now we're going to jump ahead and look at total mass emission factors. We took our number emission data and converted it to mass data. And so here you can see the total mass emission factor as a function of dilution temperature for our cellulose constituent. And likewise, we can see it for lignin and hemicellulose. Now here, again, note the y-axis is now total mass emission factor. And now we can see a clear trend with dilution temperature. We can see that as the dilution temperature increases, the total mass of particulates formed is decreasing for each of our constituent samples. Okay, now that we saw how our constituents performed, let's see how they work in the additive model when compared to real biomass measurements. Okay, so here's the number size distribution for our pine and simulated pine at a dilution temperature of 22 degrees C. So note that y-axis is the number emission factor, and we can see a similar result for each of the 4 dilution temperatures. In each temperature, we can see very nice agreement between the model and experiments as a function of each aerodynamic diameter bin. If we do what we did previously and sum up the data in each of these plots, we can see the total number emission factor comparison between the model and experiments. And what we see is that there's very good agreement between the model and the experiments in terms of total number emission factor at each dilution temperature. Okay, so how about on a mass basis? Well, here is the size result comparison between the model and experiments, and now in terms of a mass emission factor. Note that y-axis in each of these plots is now mass emission factor. I want to draw your attention to the discrepancy that I just circled. You can see that our model is over-predicting mass in large aerodynamic diameter bins compared to our experimental measurements. So when we go ahead and sum up the data in each of these 4 plots, we can see that our model is over-predicting the total mass of particulates formed compared to our experiments. And specifically, it does this at low dilution temperatures, as shown by the figure on the right-hand side. What this is attributed to is an increased agglomeration of constituent pyrolysis aerosols compared to those of a lignocellulosic biomass. Okay, so let's summarize this. We saw that biomass and biomass constituent pyrolysis emissions were sensitive to dilution temperature. We saw that our additive model well predicted the trend in size distributions of aerosol emissions from lignocellulosic biomass, specifically in terms of number emissions, and we saw very good agreement. And however, our mass emissions were less successfully captured. This work highlighted the uncertainty propagation when translating from number to mass emission factors in terms of our model, and also just in general, in that a little bit of uncertainty in number can translate to a large uncertainty in mass. And lastly, our work warrants further investigation into the effect of sampling conditions as well as reaction environment on aerosol emissions. And with that, I'd like to quickly acknowledge that this work was funded by the National Science Foundation. And with that, I'll take your questions at the end of this session. Thank you.